Okay, yeah, so my plan for today is we're going to finish the recap lecture. We almost finished it on Wednesday anyways, and then we're going to learn a little bit about references, and then after that we're going to learn about we're going to start talking about how to do objects properly in C++. At least that's my hope to get to today. And yes, lab's online today. I mean, only if you have lab on Friday. I think you were in lab yesterday, so you don't need to come to lab today. Okie dokie. Oh yes, there are 2 labs. Okay. So here's where we left off. Wait, was this where we left off? No, it was not. That's where we left off in the lab. Okay, I guess we got to go to recap. Where on earth did we go here? Okay, so yeah, we did this. Recap. Yep. We did that. Static arrays. Create a static array of size 5. The size 5 here must be constant. Good, because computer likes knowing everything beforehand, and bad because we might not know how big the array needs to be beforehand. Although this isn't necessarily bad because we might know an upper limit. This was an example, like if you were in lab yesterday, we talked about it a little bit, how we could have we might know that no more than 10 numbers will be added. So I can make a static array of size 10 and use 4 of them and just, sure, there's 6 wasted cells, but whatever. So yeah, here's an example, 5, 4, 3, 2, 1, here we go. An array, I mean, really an array should have a box that has the arrow that gets there. So given that this is valid, yeah, what is the following? An array, okay, so an array, in this case, should be, well, OX101, the memory address 101. Star an array should get us 5 because it'll go to an array, which is this memory address, 101, and then dereference it, which means, well, what's inside the box. And then, what do we got here? So we're saying an array at index 2, so an array, okay, 0, 1, 2, that's the 3, but then I guess we're putting the ampersand in front of it. So in this case, I guess we should get 103, right? Because that's the memory address of that information. And then, oh my goodness, what's happening here? So we're saying, well, let's take it one step at a time. Okay, an array at index 3. So 0, 1, 2, 3. Okay, that's this. But then we're saying ampersand. So that means memory address 104. And then we subtract 1 from it. And again, I know, like to be very clear, we know that actually when using integers, the addresses are going to count by 4s because we need 4 bytes to store these 32-bit integers. But for simplicity, I'm just doing simple arithmetic. If I want to get really precise, I should be counting by 4 in the memory addresses. But anyways, so 0, 1, 2, 3, that's the 2. We get the address of, we get 104. We subtract 1, we get 103. And then we say dereference, which means, oh, okay, what's inside? Well, that's 3. This is an exceptionally roundabout way of getting the contents of an array at 2. Dynamic arrays, well, this is how we make them. Notice there's a big difference, right? Here, like I wrote it like this, and here, like, you know, I hard-coded the values in, but here I'm creating an integer pointer, an array, and then I have to, like I say, new int, and then the size there. This is an integer array of whatever size is. And the new keyword is very important. And so this creates a dynamic array of size, and the size can be whatever we want. And this is great because we can get the size at runtime because maybe we just don't know how many strings we need to read in from a file. But this is also bad. I mean, bad's really not the word, but this can also be annoying to the computer because, you know, the computer really likes to know how much RAM it needs before. It likes it that way. And okay, that's it for the recap, I guess. Are there any questions about that recap before we go to the next thing? No? Okie dokie. All right, well, that's awesome. So you're all, you know, we're getting the difference between C++, Python, and by this stage, we should be getting comfortable enough. At this stage, though, I'm not expecting you to actually, you're not going to be C++ experts. That's not it. What I wanted you to achieve at this point is to see the similarity in that you can figure it out based on when you're writing the algorithms you were writing in 161 weren't Python. They were algorithms that you wrote in Python. So the algorithms are what's important. And then once you kind of have that experience, you just got to remember and get the syntax right for the respective programming language. I know C++ you might find annoying. Some people love it. So yeah, let's do a quick show. Raise your hand in the chat if you prefer C++ to Python so far. One person. Two people. Hey, okay, there, great. Presumably 3 people. Oh, okay. So we've got 3 people. No idea, didn't learn Python. You'd probably love it, but anyways. Okay, well, I'm glad, like, that's good that a couple of people like it. Oh, no real opinion. So, okay, some people then prefer Python to C++, and then obviously there are some people that, you know, don't really care. Sure, whatever, it's a programming language. And I guess if you take that attitude, that's actually a pretty great attitude, because then, you know, you're really programming language agnostic there. Liars. Yeah, that's a good one. You're just trying to show off. What kind of flex is it? I like programming in C++. Okay, all right, so the next thing I'm going to talk about is overloading functions, and then we're going to get to references. And references, the fact that there's something called references is why I've been careful not to call pointers references. But then again, in Java, they call everything that's a pointer a reference, even though really it's a whole thing. But I'll make it clear. Okay, actually, before this, I'm going to show you this example here. Okay, so here's some code in Python. And for those of you that, you know, maybe you've never seen Python before, it should be actually pretty self-explanatory. I heard a boop, so I just want to hear. Did I miss anything interesting? I just like the program to go zoom, zoom. Python is just, that's it. Python's too slow for you, okay. So here's some Python code. And if you've never seen Python before, but you've seen programming before, chances are you can look at this code and go, yeah, I know what's gonna happen. It's pretty like Englishy, right? All we have here is a function called add2. It's gonna take 2 parameters and then return the sum. And then outside down here, I'm saying, okay, give me a number, give me another number. So I'm reading in 2 values. I'm calling the function add2, storing the result in C, and then I'm printing out C, right? So, you know, this is perhaps a little silly example, but it's actually going to very well emphasize a bit of a problem we have. I'm gonna hit run. Okay, so give me a number. I don't know, I'm gonna give it 1 and 1, right? And we all know what 1 plus 1 is, right? It's 11. 1 plus 1 is 11. Now, why on earth did I get 11? Who knows? Anyone know? I mean, there's nothing magic going on in that code. That code is, it's very simple. What do we got? We've got 1, 2, 3, 4, 5, 6 lines of code. Really easy. They were adding strings. You're both absolutely right. In this scenario, input, you know, it automatically assumes these things are going to be strings. So I forgot to convert them to ints. If I do that, that'll fix the problem. So no biggie, you know, let's run, give me number 1, 1, there, problem solved. Great, that's the easy solution. But here's the thing. In this case, you know, if I was expecting it to take 2 integers and I got 11 when I should have gotten 2, we got a big problem, right? Like, that's clearly not correct. Because Python actually, you know, because we can put whatever types we want in here, where we know in C++ we have to be a lot more careful about the types. We have to be very explicit. In C++, if I tried to put, like, if this function was written in such a way that it was to take 2 integers and I tried to give it 2 strings, C++ it would tell me, it would be like, no, these types don't match up. You're trying to put strings into integers, that doesn't work. Where Python's happy to do so. It assumes, oh, okay, they obviously meant to add strings. Okay. So, I mean, let me give you an example of that. Def, int add2, it's gonna take int A, int B, and plus be, and I'm going to be lazy. I'm not going to actually get inputs. I'm just going to say like add 2. And if I do like 1, 1, look, it's already angry at me. Like argument type constant char star. So a string is kind of like a character array. It's incompatible. It doesn't match the integers. So that's no good. So C++, by being like strongly typed, is actually helping us eliminate potential errors. So this is a really good thing. I heard another boop. They were strings, no quotes. Never mind. No, I wanted the quotes. Oh, yes. Okay. We solved the problem by getting rid of the quotes to make them the actual integers. There, now it's happy. I assume this is what you meant. I actually meant to do it wrong. Okay, there, I can print it out. Okay, cool. Identify, int, there, problem solved. So there we go. There we go. So this is actually really good. But what if you wanted to have, like, okay, here's the thing. Okay, so I've got add 2 and it's expecting to take integers. But if I do like this, you know, like I'm curious what's gonna happen. Where the heck? Okay, I'm gonna run this and I wanna add 1.0 to 1.3 and I'm calling add 2. And I see 2, but really we know it should be 2.3. So a moment ago, I showed you how amazing it is that C++ is strongly typed. It enforces us to make sure our types check out, and it helps us eliminate a lot of errors. But now, well, like what if you actually wanted to give that function two sets, like another set of types? Well, this is actually really easily done with something called overloading. We can overload a function by giving it, by redefining it. I guess I'm going to want to return a float, by redefining it with the different sets of types. So it's not going to be angry that we have, what's wrong here? Add 2. Oh, because this is a float. Or I guess double. Should be using double. What's it about? One instance overload function add 2 matches the arguments. That doesn't. These are float. Double. Maybe I'm just, okay, there we go. There we go. Now we're happy. What did I hear? To add 2 functions. That's what I want, is I want to add 2 functions. This is exactly what I wanted. I wanted 2 functions with the exact same name, which, let's see what happens if I do that in Python. Add 2. It takes nothing. Okay. I wonder what's going to happen here. Give me a number. Oh, it looks like, okay, we got 1, 2. Uh-oh. What do we got here? It looks like it's getting confused, right? Because we've got 2 functions with the same name. But here in C++, it's all fine, because what it's going to do is it's going to say, okay, they're calling the function add2 that takes, oh, these are 2 like floating point numbers. These are doubles. So I'm going to find the one that has this name and has the matching parameter types. Now, mind you, if I do something like this, it's going to get angry again because it's going to say, well, no, there's no such version of this that takes a double and a string, which of course is true. But now we do this. This is called overloading. And that's, well, this is what this lecture is. So point of this lecture, see how we can overload functions, learn about references and how they differ from regular old variables and pointers. Okay, overloading. There we go. There we go. There we go. All of these will work. Even though we have 3 different definitions of the add function here, it all still checks out. It's happy. It's very happy about this. Now, this third one here will be problematic because it's going to probably try to run the int one and just treat these as integers. But anyways. Okay, regular old variables. Oh, okay, great. So that's it. That's all I was going to say about overloading. All right, so here's a regular old variable here. I'm creating an integer a. Okay, great. This box got set in RAM somewhere. And I said a is 6. Boop, there, the 6 is in there. I create an integer b. Okay, great. And then I say b equals a. Oh, okay, so in this case, it's going to make a copy. Whoop. Hopefully you saw that animation. I'm going to do it again because I'm really impressed with my PowerPoint animation skills. So when I say b equals a, I make a copy of whatever's in a and put it in b. See? Copy. Great. If I say b equals 7, well, okay, I just overwrite whatever was in b with 7 now. Now, notice that when I say b equals a, it just, like, it makes a copy of a. It's not like a and b are now the same thing. It's that it made a copy of the contents. But a and b are still, like, two separate variables. They're independent. Now, if I have int a, okay, great, a equals 6, okay, cool. Int star b, oh, okay, so now I've got a variable called b, but it's not going to hold an integer. It's going to hold a pointer to an integer. And if I say b equals a percent a, well, that's what we get. Cool. And if I say a is 7, well, okay, there we go. And now the important thing here is a and b are two independent variables. They're linked by a pointer from b that gets you to a, but I can go and say b equals something else, and then suddenly I lose the fact that it was connected to a in any way. So with pointers, they're still like separate variables, okay? We can use b to get to a and make changes to it, only because b happens to be pointing to a, but I can make b point to whatever I want after I pointed it to a, and then, you know, we're not pointing to a anymore. Int star a, okay, so I've created an integer pointer. Oh, and we saw this example last time. I can create a new integer somewhere in RAM and then make a pointer to it, okay. Int star b, b. Now in this case, pay special attention here. Whenever I do an assignment like this, I always copy over the contents of what's in that variable. And in this case, what's in a? Well, a is a pointer to that memory address. Whoop. There we go. So we made a copy of the pointer. We didn't make a copy of the 6. We didn't make a copy of like some chunk of RAM somewhere that held the value 6. No, we made a copy of the pointer, the memory address of what was in A and put it in B. But A and B are still independent. They're two different variables that'll get you to the same one single integer in dynamic memory, but they are still two separate variables. Oh, I guess I just fixed it. And then if I say A, okay, if I say A, but I dereference it, set it to 7, well, now it's like it's changed for both A and B, but A and B themselves are left unchanged. It's the thing that A and B are both pointing to that changed. But A and B themselves have not changed. This is important. Okay, now for references. Warning, we're going to see another more use of symbols we've been using to mean specific things used in a different context. For the most part in this class, we're actually not going to use references. References are arguably better to use than just like our basic pointers and whatnot. Like we should be using them when we can in C++. But because this class, I'm not teaching you C++, I'm teaching you like object-oriented programming and data structures. I'm going to teach this where we are using regular old pointers because most other programming languages we're used to won't use things in a reference type of way, which I'm about to show you. It's going to be done in the pointer way that we've been doing already. So references are a whole new thing. It's similar-ish to pointers, and they effectively become a second name for something. It's like if I create a variable A, and then if I make a reference variable to A, and I called it B, A and B actually are labels for the exact same variable, the exact same chunk of RAM holding something. They can't change. They will always reference the same thing. Don't need to dereference. Yeah, so best to see with an example. Int A. Okay, great. A equals 6. Cool. Now, notice the syntax here. I bet a bunch of you were kind of expecting this. You know, we used ampersand to get address of, but we use star to make pointers, and we also use stars to dereference. Are we going to use an ampersand next to the type to mean something? Yeah. So here we're saying, I'm going to have a reference to an integer called b, and it's equal to a. Now see what happens. There. Both a and b are 6. A and b are both referencing the same memory address. Like, if I were to go here, if this was memory address OX12F7GC, I don't know, A and B are both that memory address. They're both there with the 6 inside of it. I could say print A, print B, it'll print 6, and it's the same 6. If I say A equals 17, B is now 17. They're fixed. They are two variables that have the exact same name that get us to the same chunk of RAM. B equals 7. All right, well, I guess I should erase this now because, let's see. There, okay. There, it becomes 7. But both A and B are both 7 now, but it's the same 7. I didn't make a copy of anything. What I did was say A and B now get us, like, they're the same actual variable. Can I turn this off? Okay. So we can use the reference however we want. They're really handy for functions. So in this example here, we're happy, right? But remember that main, like when I start running my code, the main function appears. And like I'm kind of drawing this in a way that we can kind of visualize where in RAM, who owns what and whatnot. I create 3 variables, A, B, and C. Okay? And then if I call the add function and give it A and B, well, what'll happen is we'll go here and go, okay, great. We're going to create a new we're going to allocate a new chunk of RAM dynamically and create 2 variables, X and Y. Okay? And they're going to have copies of whatever's in A and B. Whoop. The 2 goes and the 3 goes. Look at that. You should be very impressed with my PowerPoint animation skills. It took me so long to do this. And then what's going to happen? I'm going to take the result and return it. Okay, take the result, return the 5. And that goes into the C because that's where I said to put it. And then, well, I guess actually something I didn't include was once this finishes, this disappears. It doesn't exist anymore. I mean, the 0s and 1s are still there. Just the C++ as far as it's concerned doesn't, like this doesn't exist anymore. It's gone. So that's how it works. But you'll see by doing this, I actually needed to create 2 like chunks of memory to store that information. And we saw that we could do this with pointers. In this scenario, here's what we have. We've got that. Okay, I call that function. I create a new chunk of RAM that's dynamically allocated. It's going to have the 3 variables in there, but these variables, they're not integers. They're memory addresses. So I create these 3 pointers that get us there. And then inside, I do dereference X plus dereference Y and put that in the dereference C. Well, boom, there. That's what happens. There, great. Now, let's see how it would work with references. I've got my main, so everything here is going to be the same as before, and I call add. But here, you'll notice the types are ampersand, like the int ampersand. They're references. So what happens now is basically this. Oops, I clicked 2. I create X, Z, and Y, or X, Y, and Z, whatever, X, Y, and Z. And they actually like mean, like A and X are the same thing. B and Y, they're the same thing. And C and Z, they're the same thing. They are the exact same like chunk of RAM. So when you modify it through one of the names of the variables, it's going to modify that one chunk of RAM. So this is actually a really handy use of references. Yeah, okay, great. And that's all I was going to show you with respect to the references. So, no, I guess discard. Are there any questions about that before we move on to objects? So if you set A equals 3, X will also become 3? Yes, yes. After it exists. Now, mind you, when the function finishes, the function's going to disappear, and so there's that. But yeah, when you've got a reference like A, it's like A and X. Like, you know how, okay, A equals 5, and whenever I say A, it's going to go to that chunk of RAM and get me whatever's in that like labeled thing. The reference is just like another label that gets you to the exact same one thing. Yeah. You might love references, you might hate references. You can, like, you don't have to use them. In fact, I'm going to go out of my way not to use them in this class. There are a couple of places where we have to use them because there's some like magic syntax that we need for some object stuff that we're going to do. But other than that, I'm going to avoid them intentionally, just because the pointers are going to be more like other languages like your Python and your Java. Although in Java, the pointers are called references, but really they're the pointers, not references. It's a whole thing. It angers a bunch of people. If there's nothing else, I'm going to jump on to the objects then. Look at this. We're blitzing today. This is wonderful. Oh, we got, so do you use a void function just because you are outputting A, B, and C? Let me see what you mean. Here it's, well, there's no return function, right? It's void because this function doesn't return anything. That's why it's void. Hopefully that helps. Yeah, it looks, you're probably thinking too hard. Classic programmer mistake. Don't think too hard. Yeah. Okay, all right, moving on to objects now, I guess. All right, now, I know most of you have come from 161, and in 161 we spent a third of the semester-ish on objects. So you're already all familiar with objects, but you just don't know how to make them in C++. Cool, we're gonna learn that. For those of you that didn't take 161 with me, you've got a lot of great experience with C and C++ syntax, but you don't know what the heck objects are. So here's where each group is at a different disadvantage relative to the other. You'll see that I have 83 slides here, and I'm going to try to like make sure we really take our time on this to both emphasize how we make objects in C++ and like what objects are. So it'll be good review for those people that came from 161 anyways. So, objects. Point of this lecture, review or learn concepts and terminology of object-oriented programming and see some of the cool features of object-oriented programming. And I guess that's basically it. So object-oriented programming, objects are the focus. And if you're used to like procedural programming where it's like object-oriented programming is like procedural programming with extra flair, okay? And it kind of gives us a way, like you know how we write functions to, like you've got a chunk of code that like logically is just like its own thing. I'm gonna put it in a function because there, you know, it's nice. That's where it belongs. It goes together. I just call this function and I get what I want. Objects are kind of like that idea, but at a much grander level. Like if I wanted to program a, let me think of an example. Of course I can't think of anything off the top of my head, but like I could create a car object, and in that car object, I would have specific pieces of information and actions I can tell that car object to do within my program. Just like a lot of other stuff in this course, this is best learned by seeing and doing. So we're going to be doing that, don't get me wrong, but there is going to be a lot of like pre-terminology and whatnot that we will see. So objects are things that can hold information and do things for us. Well, like I just said, all objects have, and these are all the same name that mean the same thing. Properties, attributes, fields, instance variables. Attributes is usually the word I'll use, but an attribute is just a variable that belongs to the object. And then behaviors, actions, instance methods, these are like the functions that the object can perform. And often the word I'll use here is a method. But a method is just a function, and an attribute it's just a variable, but they belong to a specific object. I heard something here. Okay, there could also be a blank program where every person is an object that, yeah, absolutely. We could do this, and yeah. All right, the objects do something cool for us. Okay, so every object that we're going to create belongs to a class. All instances of an object of the same class have the exact same properties and methods. For example, all people at St. all people at St. FX belong to the same class. Now, when I say class in this context, I don't mean like a course. I mean class. We all have first name, last names, student numbers, and an email address, okay? So the class is where we define everything that an instance of an object is going to have. So if I wanted to write code to define what it means to be a St. FX student, I'm going to make a class, and that class is going to have 4 attributes: first name, last name, student number, and email address. And we all have the same properties. So we all, like all of the students here, you all have first names, last names, a student number, and an email address. All of you have those things. But each instance of that class, each student object that we create will have different values for those properties. So someone in here, their first name is James, and another first name is Bob or something. So both people have a first name. They both have the variable, the attribute, first name, but the value associated with it are specific to the instances. A class is kind of like a template for objects of the same class. And here's a really cool way to think about it too. You can think about it a little bit mathematically, where like we are defining what it means to be a St. FX student in my code. We are defining it. We get to make it up formally, and then we follow the definition that we write. Why do we like objects? Well, it really helps with abstraction. And so like this is the example I always like to do, and you always get some smartass that raises their hand. But like the way I like to do it is like, well, ask yourself, like, do you know how the inner workings of an internal combustion engine work? Like, how do they go? And I mean, the answer is no, you don't. You don't have all the details. You don't know. But here's the thing. How many of you got here to school today by using an internal combustion engine? Now, this might be a bad example because a bunch of people might be at home. But let's say you go to the store. You don't need to know how all the components, all the inner workings of your internal combustion engine work to know how to get in your car and use it. This is like abstraction. There's details that don't matter to you. I'm going to operate my car at the level of abstraction of like, get in, turn it on, put it in drive, steer and hit the gas and brake. That's the level I'm going to work on my car, interact with my car. Now, other people might be really interested in how the inner workings of it all work, but we're going to deal with these things at a certain level of abstraction that's like easier to deal with. Another example is like the print function. You might think back to Python. You say print 15, and it prints 15 to your screen. None of you know how that works in the back end. You don't know how it's going and what the code behind that function is and how it tells the screen to turn on certain pixels with certain intensities and colors and everything. You don't know that. But you don't need to know that in order to use it and be productive with the print, right? Print function is still useful, but you don't need to know how it works. Cout. You don't need to know how it works in order to go, oh, this is just how I print stuff. And then you can use it to print stuff. There, done. And we like objects also because it helps with like logical encapsulation. This is like the idea I was talking about. We group code that kind of belongs together in a certain place. Okay, object-oriented programming. When programming with objects, we have objects interacting with other objects. This should say with each other, okay. Some objects will create other objects and use them to solve problems. Some objects will create a bunch of objects and have them work together to solve problems. And some objects will just be created to be used by other objects. I mean, sky's the limit. We can do whatever we want with these things. And again, I know at this stage, this is very high level. We'll see examples to like make things more concrete. Let's make a student object. So, okay, yeah, warning, this might take a little bit of time to make it make sense, but it all is going to come together in the end. This is an example of programmers designed this idea to do what they wanted to do with it, and there's not necessarily a really great, obvious set of steps you take to learn it. So there's going to be a lot of information that you learn, and then it's all going to come together in the end. But until it comes together, there's going to be a lot of, but why? Huh? I know it sucks, but it's kind of the way it is. And I think I found the best way to go about it, but we'll get there. So let's say I want to write a program to keep track of all the students in my class. I'm going to make a class that defines like the template. It defines what a student is, okay? And I'm going to make a class to define how I will keep track of all the instances of the students. So what I want to do is I want to define what a student is. And then I want to make an instance of a student for each person in 162. But that means I'm going to have like 30 something instances. And so I'm going to make another object that's going to kind of manage all those students for me in an easy way. So let's make a student class. So what information, properties, attributes do we want to keep track of for a student? Well, I think first name, last name, student number, and email make a lot of sense. We could add whatever we want here. We could add favorite color. We could add their favorite type of dessert. We can add whatever we want here, really. But I don't know, let's go with these four because they're simple. Actually, I guess I have a fifth one. For current average, I'm a liar. There's a fifth one. Their current average in the class, I guess. Okay. But we could add whatever we want. I'm making this up though. I'm defining what the student class is right now. I'm making this up. So I can add whatever I want. So let's write some code. So in C++, to start defining a class, we're going to want to write a header file and then a class file. The header file is where you tell C++, okay, here's all the stuff you're going to have, but it's just like declarations and definitions of stuff. In the class file, that's where we're going to actually write the code where the class actually does the stuff. Again, this will be very clear once we show you an example. So headers, what? Yeah, I know. How? I know. The way I like to think about it is the header is the what and the class is the how. Asterisk. There's a lot of asterisks here that are going to come up later in the course. But the header is defining what it's going to have and what it can do. Class is how it's going to do those things and work with those things. So a header file. It contains all the definition of things that the class will have. The class file is where we typically define how the class does its thing. And contains all of our includes for the class as well. These are like the import. It's a good place to put them. Header file, what? We didn't need that in Python, I know. Here is a header file for a student class. Here's what we have. I'm going to want string, so I'm including string. And then I say class student. That's the name of the class. I could call this Jimmy Bob 45, and then I'm now defining a class Jimmy Bob 45, but that's pretty silly. I mean, a good name for this class is student. And then I've got this thing here called private, which I'm going to talk about in more detail in a moment. But private are, like at a high level, private are the attributes and functions that only this class knows about and can use. The public things, the things that we put under public, these are what other classes and other chunks of code can access within an instance of a student class. I know a lot more weird, confusing information, but again, through example, we will see. So private, public, yeah. Public, private are visibility keywords. They tell C++ which parts of the code can and cannot be seen by other bits of code. They will likely be confusing, but they'll become clearer sooner on, I know. Here I'm defining my first name. The convention, anything private, we start with an underscore. And yeah, so because we're creating an attribute here called first name and it's private, I usually, like the convention is, and there's a billion other conventions out there, but the convention I like to follow is underscore what that attribute is called. And then we've got last name, also underscore student number, email, and current average. Okay. So I've defined their type and said what they're called. But like I'm not doing anything here, I'm just declaring them. And then under here, I've got a special function. Actually, I have two special functions or methods. One is the constructor and one is the deconstructor. The constructor is a special method that tells the computer how to, it tells the computer how to go create and set up this object for use. More on this later. And a deconstructor is the code that says, okay, we're done with this object. How do I get rid of all the stuff it's created if we needed it? So for example, imagine our student object allocated a bunch of stuff in dynamic memory with the new keywords. Well, the deconstructor is going to want to delete all those things. We'll see examples. Don't worry. I do recommend, I mean, when I started learning this stuff, I just kept a copy of everything I ever wrote, because I always forgot, like, wait, how do I do this? How do I write this, the header? I mean, the syntax. I think for like my first 10 assignments, I just started by making a copy of the previous assignment and then making changes I needed to get things to work the way I needed them to work, because I would never remember this stuff. So here we go. Now within the class file, we would say something like include student.h. This is the header file. And then from the student namespace, like from student, I'm implementing the constructor, the thing called student. And I'm defining all these things. And then I'm also defining the deconstructor. And there's nothing there for now. It's fairly useless. Constructor is used to create the object. The constructor is what the computer uses to make the object in RAM. We also set up variables that we like in the constructor too. Here we just have a default constructor. It sets up default values, okay? We can overload this as many times as we want, but here's a default one. If someone wants to create a student object, by default, its first name will be John, then last name is Doe, and student number will be all zeros and whatnot. And they've currently got 100 in the class. And the deconstructor has nothing in it. But like I said, if we made anything in the constructor, or if there was anything within the class that created something in dynamic memory that needed to be deleted, the deconstructor is where we would do that. Sorry, that's actually not correct. Really what I mean to say is, if we want to delete a student object, but the student object has stuff currently in dynamic memory, when we delete the student object, it runs the deconstructor, which would then take care of deleting all the loose ends. Again, I know we're in this stage of learning all these weird things, and we haven't come together yet. So just sit tight. I don't know what the difference. I'm showing a comparison. So in C++, here's what my class file looked like. In Python, here's what I would write instead. You know, there's a lot of similarity there. There's a lot of differences. We don't need the header. C++, we need a header. We don't need a deconstructor in Python, but we do in C++. And I guess in C++, the name of the class is what we call our constructor, where in Python, it's underscore underscore init underscore underscore. Okay. So we have enough code to define the object, but at this stage, the student class is absolutely useless, but we can still test out our code to make sure everything is okay so far. So here's what I'm going to do. And I would actually encourage you to follow along if I don't move too fast. So here's what I'm going to do. I'm going to go and copy all this. This is my code. So I'll delete this, and I don't really need this for now. So here's what I'm going to do. I'm going to right click on my class, add class. Okay, and my class name is going to be student. Also, convention, always start your classes with an uppercase. And okay, yeah, so always start with an uppercase. In Visual Studio, when I do the add class option, it's automatically going to create the header file and the C++ file. That's like the class file. It's going to create those for both files for us. So I'm going to say okay, and it's doing its thing. And you will see there's a folder called header files that I open up, and there's a folder called source files where our main was, and also now the student class. And it's set up for us. Like, it's got some stuff in there already for us. Pragma once, if you're using Visual Studio, just leave this there. I'll explain what it means at another time. But here's what I'm going to do. Just copy, paste, there. Great. Great. I've now written my student header. I'm saying, okay, class student. I guess I can put this here. The private attributes, well, here they are. These are all attributes. They're just variables. Public, these are the two methods I have. Okay, cool. This is dumb. It's useless, but there it is. And you'll even see, what does it say? Function definition for student not found. Well, yeah, that's because I haven't written it yet. So I've copied that in, and I'm going to go to the next one and copy this in. Nope, student C++. There we go. So we can test this now. I've now started making a student class, and all I did was copy and paste the code into like Visual Studio, and it's there. We've got the building blocks of our thing. So the class files goes in solution where, well, yes. What you do is like you'll do class files go in the source files. Really, if you just right click on like the name of your project and do add, you can click class and then it comes up with this like fancy little box that you just type in the name and then it does stuff for you. And it'll automatically put the things in the right place for you. And okay, and I'm saying we can test it. So here's what we're gonna do. Oops, I'm gonna copy all this. I'm going to put it into my hello world. There we go. So I've got my IO stream, I've got my string, and I'm including student.h because student.h is where we say everything that is going to exist for a student file. We don't put student.cpp. We need the .h. The .h is what we need. And you'll also notice that the things that we're including, like these files, we have quotes, like as if they're a string. Where the other ones we use like the less than and greater or like, you know, triangle brackets. But when we're including something from like in here, it's quotes. And here's what I'm doing. I'm doing actually here. I'm actually creating a student in two different ways. Generating code, yeah. Okay, let's run it. Okay, nothing happened. That's what we expect. Now, in here, I'm going to show what's happening in RAM though. So in this example, I'm creating a variable called aStudent, and it's a student object, and it's gonna be put in like static RAM. Or like it's gonna be put like the computer's happy with this. So there, we made aStudent, it's gonna hold a student object. Great. But down here, I've got something completely different. I'm creating, and by the way, this way I'm doing it is how we're gonna do most of the stuff in this class. This is the better way. That's entirely not true, but this is the way I'm gonna make you do it in this class. I'm making a variable called whatAmi, but it's a pointer to a student object. It's not a student object. And then, you know, new student. So somewhere in RAM, we called the constructor, it created that object, and then whatAmi points to it. And you know what? I'm gonna add one thing to our code. I'm gonna go to our constructor. Now, whenever we do something like in our main, when I said, okay, new student, when I called this here, the name of the class, this actually runs this code. It runs the constructor. So first name is set to John, last name Doe, student number. All the code in this function here, this method, runs. And to prove that, I'm going to have it also do, oh, I guess I'll have to include IOStream because I didn't include it here. Header, okay. There. Okay. And then this should be happy now. Okay, so to prove it that this is going to run, this constructor is going to run when I, you know, run this code, I put in like a print here. So let's see, I'm going to rebuild. Okay, and I run. And we see I ran. We saw it twice because in here, we actually called the constructor twice. When we created this student, it made a default student. We created something of a student type, created a variable called aStudent, and then we ran the default constructor here, which said all these things, and then it printed it out. And then in the next down here, okay, create a student pointer, call it what am I, and have it point to a student that's created somewhere in dynamic memory. And that's why we also see this function here, the constructor, being run again. You can really put whatever code you want in the constructor, but ideally it's used to just kind of like set things up. Anyways, we are out of time, so hopefully you'll learn something, but we are very far away from having a good full understanding of objects. For those of you who already have the object experience, you might feel comfortable enough to start sinking your teeth into some of those details. But for those of you that haven't done objects before, I know we're still a little ways. Like, we got to finish these sets of slides to like really see how it works together. Anyways, that's it for today, and I hope you all have a wonderful weekend. Or if you're in lab, I'll see you in lab. Okay, bye.